Guerrilla RF offers two flavors of our SDARS reference design. One is a dual saw or a dual filter reference design, which is best for co-located environments such as shark fin antennas, where there's other cellular and Wi-Fi signals that are present. You definitely need to use a dual saw SDARS reference design. If you are not in a co-located environment and you are far away from any type of cellular or Wi-Fi source signal, a single saw SDARS solution could also work. I always like to default to the dual saw reference design because it's our most worked on reference design. It's our most requested, and it's our most optimized reference design. Other SDARS offerings I've seen on the market are typically modules. Modules are very limiting because once the module's created, it's locked in. So any changes in technologies or SDARS specifications, if you have a module, it's really hard to adapt. With our discrete reference design, we can adapt in an instant. If there was a new spec that came out from Sirius XM radio, we can quickly accommodate that. If it's as simple as changing a match or searching the marketplace for a different performing filter, or internally if we need to select a different gain step, such as our LNA, if the linearity was failing for some reason, or if there was some other requirement that we were failing, we have a huge library of LNAs that we could attempt to meet any spec requirement change that ever came along. The ability to have a discrete circuit, another advantage of having a discrete circuit is our use of RF360 Qualcomm SAW filters. We use a first stage filter and a second stage filter from Qualcomm. They are very receptive to changing and improving their filter over the years, and that has helped Guerrilla RF keep a competitive advantage in the SDARS marketplace. Their first stage filter is extremely low loss with great out of band blocking attenuation, and this is critical, and you do not want to allow signals that are being generated from cellular or Wi-Fi or other sources being amplified on the first stage LNA in the SDARS circuit. So the first filter will do a really good job of attenuating those out of band signals, and we more than exceed the Sirius XM spec for all out of band signals for the whole SDARS bandwidth. So up to 5,900 megahertz and just about higher, all the way down to the lowest requirement. You always have to put in a whole lot of power into the first filter in order to exceed the Sirius XM spec. So the first filter is extremely robust and valuable. The low loss of the first filter combined with the really low noise figure of our 2070X series LNAs will give you the best noise figure in the marketplace. Our noise figure is 0.8 dB and lower. The Sirius XM spec is 0.8 dB with a contingency of plus or minus 0.2 dB of error. So if you consider that, they're kind of saying their spec is 1 dB. If you're 1 dB, then you're compliant with Sirius XM radio's noise figure. And we know for a fact that we are, 20% lower than that or better. So the first consideration with any Sirius XM radio circuit that you're going to implement is going to be noise figure, and we are very well below that. I would say the second thing you need to consider is linearity. In this first filter, with its really good out-of-band attenuation and its really good insertion loss, allows us to be extremely linear, well above specification on all linearity requirements for Sirius XM radio. So after the second stage of this Sirius XM of our SDARS circuit is a second stage filter, which is actually a lot more lossier, which we don't care about because our noise figure is already established by our first filter. So our second filter has a lot more loss, but it does a really good job at meeting the requirements of the rejection ratio. Yeah, our intermodulation rejection ratio, the IMRR spec from Sirius XM, we more than meet and exceed that spec. And then we incorporate a second stage LNA. We usually use one of our 4000X family of LNAs for that for our second stage. Usually a 4002 or 4012 or 4014, and these vary from application to application, vary on gain requirements. They vary on if someone for some reason needs to be more linear, we could use a part like our 4014. If somebody is satisfied with our typical standard BOM performance, then a 4012 is good. If somebody can't, these parts I just mentioned are all DFN6. If somebody doesn't want to accommodate a DFN6, we have DFN8, some DFN8 versions of these, such as the GRF 2112 is a good second stage option as well. So package-wise, I guess something I haven't touched on, package-wise, we can really accommodate any package combination somebody would want, whether they just want DFN6s only, DFN8s only, or a combination of the two. Typically, we always stick with our DFN8s. The larger package size offers a bigger ground area, lower inductance, better thermal relief, and better stability. Some parts in the DFN6 package that have a lot of gain could cause you a little bit of a stability issue, but that could be a different topic. Oh, any SDARS circuit that's implemented on a customer application, feel free to send it to Guerrilla RF. Myself or someone else will optimize any tuning requirement that you have. When you translate an ideal EVB like we have here in our lab, it may not transfer 100% to a mass-produced EVB like you might integrate in an actual product. And a common thing that I do frequently is receive customer boards and make minor or major changes and layout suggestions for any customer that needs it. And that is one of the big contributions or differentiators that we have here at Guerrilla RF.
Thank you so much for watching. If you'd like more information, please email us at sales@guerrilla-rf.com. And don't forget to subscribe to our channel for more content from Guerrilla RF.